bj plus t are also disjoint. Obviously, we just shift everything. And this implies that sum of f, and they have the same length, bj plus t minus f of aj plus t, and they don't need absolute values because we assumed f is increasing, is less than epsilon, and this implies that sum of, let's see, so it implies, okay, let's see, what do I want? Okay, good morning everyone, and we'll try something new today. I'm going to use my iPad instead of the Surface Pro, and also I'm going to use the landscape orientation. So we're going to assume that we have two boards and see how it goes, because it has been brought to my attention that if you're using an iPad, especially a smaller iPad, then the portrait orientation is inconvenient. Okay, and we're starting a new topic, which is kind of the last qualifier topic in this course, and it's called absolutely continuous functions. And I'll go ahead and start with the definition right away. So f will be defined on a closed interval, will be finite, and we'll call it absolutely continuous if for every epsilon there exists a delta. And now you would expect that I say that if 2 points are close enough to each other, then the values of the function are close enough to each other. But now we'll do something completely different. We'll also say that, okay, so such that, so there exists a delta such that for every finite collection of intervals aj, bj of pairwise disjoint intervals, we have sum of the lengths is less than delta, implies sum of the difference in the values is less than epsilon. So if you think about the regular continuity means that this holds only for one interval. Now we ask for it to hold for any finite number of intervals. Okay, and so example, so just a warning that an absolutely continuous function is something we have never seen before, so that's a completely new notion, and a very strong notion actually. So example, f is Lipschitz, then it's absolutely continuous, and we will abbreviate it to AC. Why is that? It's because sum of f of bj minus f of aj is less or equal. And what does Lipschitz mean? It means that difference of the values is less than or equal than a constant times bj minus aj, and the constant factors out. So we can take delta equal to epsilon divided by c, for example, or we can take 10c to be safe, and everything's fine if this sum is less than delta, then multiplied by c it will be less than epsilon over 10, so definitely less than epsilon. Okay, so important theorem is that f is AC implies that the total variation of f is finite, so an absolutely continuous function is always of bounded variation. Moreover, so what do we know? We know that a function of bounded total variation can be written as a difference of two increasing functions. So here I'm not saying anything new, provided we proved the first arrow. So are increasing and also absolutely continuous. So if a function is absolutely continuous, we can write it as a difference of two increasing absolutely continuous functions. Okay, so proof. So for total variation first. So for total variation, it's actually easy. So we'll just take epsilon is equal to 1 and find the corresponding delta. What do we know? We know that if sum of bj minus aj is less than delta, then sum of f of bj minus f of aj is less than 1. Okay, so now split the interval AB into n intervals of length approximately b minus a divided by delta. Sorry, no, or yes, hang on. Okay, so n should probably be sorry, n should be b minus a divided by delta of length delta of length approximately delta. So n is approximately b minus a divided by delta. Here it is. You can fill in the details. So here's the picture. So here's AB. I take the first interval of length delta, the second interval of length delta, 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 delta. Then at the end, so this before the last one also has length delta, but this last one might have length less than delta, which is fine. And in any case, n is something like b minus a divided by delta, or maybe b minus a divided by delta plus 2. It doesn't matter. What matters is that n is finite. So I'll eventually get a very bad estimate for my total variation, but it will be a number. All right, so then what do we know? We know that the total variation of f, this is what we proved last time, is equal to the sum k from 1 to n of total variations of f restricted to the interval ik. So the kth interval will be called ik. So this is I1, this is I2, this is ik. All right, and on ik, so ik has length less than delta, and so on ik, we can estimate the total variation just using absolute continuity. Here is how we're going to do this. So on ik, let's say that pk is a partition of ik. Then sum of the length of the intervals in this partition of intervals defined by pk is exactly equals to the length of ik, because this is what's a partition. So here's ik under the microscope. Partition starts here, then it splits ik into some intervals, maybe small ones, maybe big ones, then it adds here. So if we add all the lengths of the intervals in this partition, we'll get exactly length of ik, and length of ik is less than delta. So this means that from absolute continuity, sum of the difference of the values of f, so xj's are in this partition, is less than epsilon, and epsilon is 1. Okay, I'll scroll up. Here is my epsilon. It's equal to 1. So this is less than 1, and this implies that the total variation of f restricted to ik, this is true for any partition, so total variation here is less than 1, and this implies that the total variation of f everywhere is less than n, which is less than infinity. So n, I remind, is approximately b minus a divided by delta. And this is it. So f is definitely of a bounded variation. All right. So now we need to prove that f can be split into a difference of two functions which are increasing and absolutely continuous. And we already know that f is equal to phi, let's see, psi minus phi, where psi is equal to f of x plus the total variation of f restricted to ax, and psi is equal to this total variation. So I'll be done if I prove that these functions phi and psi are absolutely continuous. So in fact, because f is already absolutely continuous, if I show only that phi is absolutely continuous, then I win. Because psi is f plus phi, and if this is AC, and if I prove that this is AC, then the sum is definitely AC. That's not hard to check. So let's prove that phi is absolutely continuous. All right, so, well, we'll take, so we fix an epsilon and take delta for epsilon over 2 from the absolute continuity of f. So that is sum of bj minus aj is less than delta, and their disjoint implies that sum of f of bj minus f of aj is less than epsilon over 2. I can always do this because I can do this for any epsilon, so in particular for epsilon over 2. All right, so let's see. So let's take any partition of aj bj and call it pj. So these intervals are disjoint, or at least disjoint except for the endpoint, because we were talking about open intervals, so they can meet at the endpoint. But except for the endpoints, they're disjoint, and so pj's are also disjoint, except maybe for these connecting points. Okay, so what is the variation of f over pj, and then I sum over all j's? Well, so pj is a partition of aj bj, so sum of the length of the intervals in pj, as before, is exactly equal to the length of aj bj. And so sum of all the lengths, because they're not overlapping, is less than delta. And so this is less than epsilon over 2. Okay, because sum of length of the intervals defined by pj is exactly bj minus aj, so sum of all lengths over all pj's is this, which is less than delta. And so sum of the values of f is less than epsilon over 2. Great, and now take the supremum over all pj's, and we'll then, so pj's are absolutely independent, we get this. Okay, and what is ij? Ij is aj bj. Okay, however, we know that this, and this we proved last time. Okay, I'm not using my right hand side board. So we know this. So this is phi of bj minus phi of aj. And we're done. So we know that sum of this is less than epsilon over 2. The reason I need epsilon over 2 is that because actually I lied to you somewhere and I have less or equal. I have less or equal here. I have less or equal here. Because when we take the supremum, less can become less or equal. So I have less or equal here, so I have less or equal here, but it's definitely strictly less than epsilon. And now I can almost imagine your sad faces. So let's go a little bit back and see that we've done everything we needed. So we fixed an epsilon. We took any intervals that are not overlapping and their sum is less than delta. For our chosen delta, we are free to choose delta. So we took any family of intervals with total length less than delta, and we proved that the total oscillation over these intervals is less than epsilon. So we win. All right, now we need to sort of cover the hole that I left. So Royden has this notion of uniform summability, which is typically not needed, which is a very strong notion, and it is used to pass the limit under an integral, but it is very rarely possible to use it. And here is pretty much the only place where it's used, so we'll patch this hole and state it now. So definition. So family f whatever, let's index it by h, and let's say h is from 0 to 1, so it doesn't even need to be countable, doesn't really matter, is uniformly, you know what, I don't even need 0, 1, I just need h to be in some set of indices, is uniformly summable if for every epsilon there exists a delta such that if the measure of a is less than delta, then the integral of f sub h over a is less than epsilon for every h in h. So why uniformly? Because delta doesn't depend on h. And why? What does it have to do with summability? Well, remember that if a single function is summable, then this arrow holds. This arrow was called absolute continuity of the integral with respect to measure. So if you go like 50 pages back, you'll find the absolute continuity of the integral with respect to measure. It's exactly this. Now we call a family uniformly summable if these integrals are kind of uniformly continuous. So if the measure is small, then all the integrals are uniformly small. Okay, and here's the theorem that f is absolutely continuous on AB implies that the family D sub H of F is uniformly summable, where DH, I'll remind, is f of x plus h minus f of x divided by h, with the usual convention that for x bigger than b, we define f of x to be equal to f of b. Alright, so why do we need this? Well, because as I said, it will significantly help us to pass to the limit under the integral, and when we pass the limit as h goes to 0, we definitely get the derivative of f. So we somewhat want to improve on this Fatou lemma that we used to show that integral of the derivative is less than f of b minus f of a. So if we're able to write equals there, we will prove that the integral of f prime is equal to f of b minus f of a. But to write an equality, we need something stronger than the Fatou lemma, and this is the stronger thing. So we'll actually be able to write that the limit of the integral is equal to the integral of the limit, and so everything will be equal. All right. So let's see how it's going to work out for us. Well, let's prove it first. Okay, so first of all, f is equal to f1 minus f2. f1 and f2 are increasing and absolutely continuous. Moreover, dhf is equal to dh f1 minus dh f2. So we only need to prove it for one of them. If this family is uniformly summable and this family is uniformly summable, then the difference is also uniformly summable because absolute value right here, we have another arrow pointing, so the absolute value right here will be less than sum of the absolute values of these two friends, and we'll get something like 2 epsilon, which is fine. Okay, so without loss of generality, we can assume f is increasing. And f1 and f2 are still absolutely continuous, so we don't lose anything here. Okay, so let m1 of a be less than delta. Then we can approximate a by a g delta set with measure of g minus a equal to 0, but because measure of a is finite, it just means that measure of g is equal to measure of a. Okay, so the only, well, actually, always. And also, because we know that the integral of something of measure 0 is 0, we have integral of a of anything is equal to integral of g over g. So in fact, in the definition of absolute of uniform summability, sorry, I need a third arrow. So in this definition, we can only consider A to be a G delta set. Now, furthermore, we know that G is G delta, so it's a union of a decreasing sequence of an open sets. And we can also assume that they have finite measures easily, because G has finite measure, so this can also be assumed to have finite measures. And each Gn is, because it's open, it's a union of disjoint intervals. Now some of you like to catch me about the disjointness, so we can, for example, take disjoint union of half-open intervals. Half-open will be fine. We can also take union of open intervals. It will still be disjoint. They won't cover Gn, but they will cover Gn almost with a measure zero error, which is also fine. Okay, and so we know that measure of G is equal to the limit of measures of Gn. So at some point, for some n, we'll get measure of Gn is less than 2 delta, for example, right? So measure of G is equal to measure of A is less than delta, so measure of Gn will eventually be less than 2 delta. And this means that the measure of any interval that participates in Gn, so any interval from here, is also less than 2 delta. And my point is that if we now prove this, for any interval with measure less than delta, then by countable additivity of everything, of the measure and of the integral, we'll have the same thing for Gn, and as soon as we have the same thing for Gn, we'll have the same thing for G, because both measure and the integral are continuous from below, and as soon as we have everything for G, we'll have it for A, because everything for G and A is the same. So this implies that, okay, so actually I said one wrong thing. It implies that we only need to check this arrow, integral of over A of dh f dm1 less than epsilon for a disjoint union of intervals. Okay, that's the correct statement. So if we know it for disjoint union of intervals, then we know it for any open set. So we know it for Gn, and then we know it for G, and then we know it for our original A. And this actually explains why do we need absolute continuity, because absolute continuity enjoys disjoint unions of intervals. Okay, so let's assume A is this, or I could even take half open, doesn't really matter, and sum of bj minus aj is less than delta. Well, what does this imply? Well, we already know that it implies that sum of absolute value of, actually f is increasing, so we just know that it implies that sum of f of bj minus f of aj is less than epsilon. Okay, so let's recall this. Let's recall that if we integrate our derivative from u to v, it will be 1 over h times the integral from 0 to h of the function g dm1, and g of t is equal to f of v plus t minus f of u plus t. This is very similar to the identity we had. I'll just write it here. So similar to what we did to prove that integral of f prime dm1 is less or equal than f of b minus f of a when f is increasing. So if you look there, you'll essentially find the proof of this statement. Okay, so now if we have these intervals disjoint, if the half-open ones are disjoint, then these are also disjoint. Then the shifted intervals aj plus t, bj plus t are also disjoint. Obviously, we just shift everything. And this implies that sum of f, and they have the same length, bj plus t minus f of aj plus t, and they don't need absolute values because we assumed f is increasing, is less than epsilon, and this implies that sum of, let's see, so it implies, okay, let's see, what do I want to say? I want to say that this implies that g of t is less than epsilon. For every t in 0h. Why is that? Yeah, so, sorry, yeah, for every t in 0h, where, you know what, it was just wrong to use g. Let's use something else. I cannot use h. Let's use capital F of t, where capital F of t is equal to sum of f of bj plus t minus f of aj plus t. Yes, so sorry, I got confused because in my notes I call g. I have g for two different things. Okay, so this is f. So why is it less than epsilon? Well, just by definition, because this is less than epsilon. And it actually doesn't depend on t. All right, and so what's integral of dh of f over a? So remember that a is a disjoint union of intervals. I can write open because the endpoint doesn't matter. Okay, now integral over the interval, here it is, and here it is. So this is 1 over h, sum over j, integral from 0 to h doesn't depend on j, of f of bj plus t minus f of aj plus t dm1 of t, I should write. Okay, now I can take the sum inside. This will be 1 over h integral from 0 to h f of t dm1 of t, and f is less than epsilon, so this will be less than 1 over h integral from 0 to h of epsilon, and this is just equal to epsilon because we're integrating from 0 to h, so h cancels out and we get the epsilon, and this is what we wanted. So integral over a of dhf is less than epsilon. So what we achieved here is this. If A is a disjoint union of intervals, which means that this is true if A is an open set, and if this is true for any open set, then It's true for any G delta set because measure of a G delta set is limit of measures of the open sets, and if it's true for a G delta set, then it's true for every set. Now there is one gap I have. So an open set is actually an infinite union of disjoint intervals, and I've only did it for a finite union. But if you want to do it for infinite union, it's equally easy because you just pass to the limit. So if you have an infinite union, you just take finite unions, you take a sequence of finite unions, it's going to be an increasing sequence, and so you pass to the limit one more time. So we're done. And now this will imply an important lemma. Important lemma says that if a family Fn, now it will be countable, is uniformly summable and measure of A is finite, then Fn converges to F almost everywhere implies that integral of F over A is equal to the limit of integrals of Fn over A, dm1 here. In particular, F is summable. Okay, so this is like sort of a Lebesgue dominated convergence theorem, except that instead of some control on Fn's, some explicit control on Fn's, we have this uniform summability. Alright, so let's prove this. Okay, so first, because we know that the measure of A is less than infinity, we can write A as a finite union of sets AK such that their measures are less than delta and AKs are disjoint. So I'll leave it as an exercise. It's like almost obvious, it's especially obvious if A is a bounded set. So if A lies in some huge interval, then this is very easy, just split this interval into many pieces. But A theoretically can be infinite, like can be unbounded, and still a finite measure. Then you need to be a little bit careful. So then you need to find this huge interval that works first. Okay, what do we know then? We know that the integral of Fn over A is equal to the sum of integrals over AK, and measure of AK is less than delta, so integral of Fn over AK is less than epsilon, so this is less than epsilon times n. And n is finite, that's my only concern. So this means that the integral of absolute value of f by Fatou lemma is less or equal than lim_inf of integrals of Fn, which is less than epsilon times n, and this implies that f is summable. So we can take, for example, epsilon equal to 1. Then n is huge but still finite. Okay, so now our next reduction, without loss of generality, we can assume f is non-negative, fn's are non-negative, f is 0, and so fn's converge to 0 almost everywhere. Why is that? Because we can do fn minus f, and this would be a horrible thing to do if f wasn't summable, but because we already know that f is summable and it does depend on n, and it means that fn's are uniformly summable, implies that fn minus f, this family, is also uniformly summable. So this is because fn's are uniformly summable, and f summable implies fn minus f, even with the absolute value, is uniformly summable. This I'll also leave as an exercise, but that's a trivial exercise. Alright, so we'll finish this proof and call it a day. Okay, so now we take integral of fn over a and split it like this. So I will choose a0 later, but what's important is that if measure of a0 is less than delta, then this second integral is less than epsilon. Okay, and now, surprise, surprise, we'll hit it by Yegorov's theorem. So I lied to you, I said it will never use it. Well, here's the place where we'll use it. So there exists an a0 in A with small measure and fn's go to 0 uniformly. So that's what Yegorov does. It says that if we have a set of finite measure and we have pointwise convergence, then we have uniform convergence on a big chunk of our set. Alright, and so this implies that the integral over a0 is less than epsilon, but it also implies uniformly, sorry, I forgot an important thing, uniformly on a minus a0. And fn converges to 0 uniformly on a minus a0 implies that the integral of fn a minus a0 converges to 0. This I'll leave to you to check. That's what you probably did exercise when you took some advanced analysis class. So your first or second proof-based class definitely should have contained this. I'll leave it as an exercise, but uniform convergence is very strong. So uniform convergence implies that we can interchange limit and integration. And so we win. So we now have this. Fn dm1 plus epsilon, and this goes to 0. So this means you can pass to lim sup, for example. Is less or equal than epsilon for any epsilon. So this lim sup is less or equal than 0. And fn's were non-negative, so it can be less or equal to 0 only if it is equal to 0. And so we win. Okay, so before we call it a day, we'll call it a day right now. I'll state the main theorem. So the main theorem is that f is absolutely continuous on AB, implies that the integral of f prime dm1, which exists, by the way, because f is an absolutely continuous function, implies that it's a function of bounded total variation, and function of bounded total variation is differentiable almost everywhere, and the derivative is summable. And now we get the Newton-Leibniz formula. So this integral of the derivative is equal to f of b minus f of a. So this is all for Wednesday. I really hope that today's stream got better, but anyway, the comments are open. The chat was active, I should say, or if you're watching it before the live stream, the chat will be active because I wrongly assumed that making this video suitable for kids makes it better. It actually made it worse. So anyway, I'll stream it on Wednesday and hope to see you there. So bye bye.